Hello and welcome back. I'm Babak, and this is the second series of lectures on large-scale hydropower. Now we are going to take a look to water turbine as the major component in hydropower plant. You've seen these impulse turbines before on lecture series 1, so I'm not going to repeat this. They are more applicable to medium to small scale hydropower plants. For large scale power plants, we have reaction turbines that are based on Francis, Kaplan, Darius, and pump turbine as a subcategory to the reaction turbines. We start with Francis turbine, and then Francis turbine is the most widely used turbine for large scale power plants, and they cover a very large band of flows and head for electricity production. So we start with an explanation here. Water comes from a penstock on the inlet side. It rotates in the volute, and then it goes to the stationary vanes, and then we have these adjustable guide vanes, and water goes toward the runner itself. The runner is in fact the blades and the shaft, which is called the runner in the turbine. Here you could see the section of the turbine. The role of the guide vanes is in fact to guide water and give it a tangential velocity vector before it goes to the runner type in order to deliver energy to runner blades. Water released into the draft tube after giving its energy to the runner blade. So here you could see an illustration of the Francis turbine. So it's in fact the blades. Normally they are between 12 to 44 or to 24 blades inside the runner, depending on the design. You could see the guide vane mechanism here, and this mechanism on the top makes it available in order to adjust the guide vane's opening. So in fact, each guide vane here could rotate along the axis, and then this opening is adjustable. Maybe you could see it more better on the picture on your right side. So the guide vanes, they could rotate along their shafts here, and this makes it available to have different opening for the guide vane. And this enables regulating inlet flow toward the blade. So in fact, the amount of flow that goes into the turbine could be adjusted by guide vanes. This is a section of a real project. So you could see a man standing here. In larger scale projects, the size could be very impressive, in fact. So you could see the turbine, which is colored in gray here, the blades here, the guide vanes, and then this is the volute all around the turbine. This volute is actually in concrete, so it's cast in concrete. Water comes in, and then it goes around the turbine. So the turbine, the runner itself, it's cooled to the generator, electricity generators on the top. These are photos from the different runners. It's good to have a sense of the size and the magnitudes of the power production. So this is almost 62 megawatt runner, which looks at this size. On your right side, you could see 400 or 469 megawatt runner blade in Sweden, and then compare it to the size of the people that are standing next to it. This one shows the turbine, the Francis turbine, inside a power station. So you could see there are many auxiliary equipment around the turbine itself, the turbine and generator, such as cranes, such as controlling gates here, draft tube. So I start from the inlet penstock here. Water comes in, and then it rotates around, and then it is released on the downstream of the turbine. So this one here in fact shows a bypass. So if for any reason the turbine or the generator is under maintenance or some other complementary work within the turbine stage, then water could be bypassed through these valves here. But in normal case, water goes in and then it goes out from the draft tube. The next turbine type is coupling turbine, and this is an axial flow. So in fact, flow comes axially toward the coupling turbine as it passes. It's more suitable for lower or medium head. And then the efficiency is around 90%. It has a mechanism inside that enables the rotation of blades. So each blade could rotate along its axis here, as you could see by this mechanism, which in fact enables adaptation of the turbine performance to the incoming flow. This one shows another example here. So you could see water comes in along the guide vanes, and then it goes axially toward the turbine itself. And that's why it is called an axial turbine. And again, it is connected to the generator on the top. So here you could see the mechanism, the rotating mechanism, which is in fact inside, but these pins here connecting that mechanism to each blade here. And then this is the same runner which goes inside the turbine house. So again, water comes in, more or less it's the same concept as the Francis turbine, but the shape and the geometry of the turbine itself is different from Francis turbine. If we take a look to each blade, a section of this blade, you could see water comes in and then it leaves the blade. There are many technical terms. If we take a look to the design of the turbine itself, and then it deserves a whole dedicated course for designing of a turbine. But what is important here, this is the core, and then the angle between the core and the axis of the turbine, it is called the stagger angle. So this angle is in fact adjustable through the mechanism in coupling turbine. And then it enables adaptation of the best efficiency point according to the flow. If you take a look to this chart, on the y-axis this is the efficiency, and then this is the relative flow. So in fact, the different flows that comes in, you could see it along this x-axis. So if flow decreases, for example, then the angle could be changed, and then this curve could be adjusted to the new coming flow. And also the guide vane angle is also adjustable. So this has an impact. The combination of this enables the coupling turbine to adapt itself, to adapt its best efficiency point to the incoming flow, and then it makes it a more suitable option if flow varies quite widely in some project schemes. The propeller turbine is a subcategory of a coupling turbine. In fact, it's the same as a coupling turbine without that adjusting mechanism. So there is no adjusting mechanism for this coupling turbine. Darius turbine is just that you know and you hear the name. It's a combination of the Francis turbine and a coupling turbine. In fact, it is intended to fill somehow the gap between the Francis and a coupling turbine. So they have the geometry design is like more Francis turbine, but they have the adjusting mechanism of a coupling turbine. This chart here shows the efficiency, and then on the x-axis you have the relative discharge. For example, for the propeller, because there is no adjusting mechanism, you could see that the efficiency drops dramatically by changing the flow conditions. So efficiency drops rapidly here. While, for example, for a coupling turbine, thanks to its adjusting mechanism, the turbine can adapt itself to the varying flow conditions. And more or less, Francis turbine has more or less the same trend or behavior. Then comes the bulb turbine. It's suitable for very low head, mainly in the order of 5 meters or so. So the turbine itself, the entire generation is mounted inside the water passage, as you could see here on this photo, and the turbine blades itself is located at the back here, so water flows in this direction and rotates the flow. It's not common to have these bulb turbines for larger scale projects, so we just pass through it. And then finally, the pump turbine or reversible reaction turbine, they are the turbines that are in fact pumps at the same time. So depending on the rotation, the direction of rotation, they could act both as a pump or a turbine. And they are common to be used in pump storage schemes, as we discussed before. So here, again, you could see a section of this, the whole entire pump turbine. The runner here, you could see the shape is or the geometry is different than the Francis turbine. It also includes some aspects of the pump runner blade. So in fact, it could be used at the same time as a pump or as a turbine, depending on the direction of rotation. I would like to take the opportunity here just to show this scheme here. You could see the pump turbine here. As we said, larger scale projects are grid connected. So in fact, for the pump turbines, they are acting in both directions, making electricity, generating electricity, and injecting it to the grid, or taking electricity from grid and then running as a pump and pumping water toward the upper reservoir and store it to be used for later for later time. And as an example here, you could see that wind farms are also cooped to this grid. It could be a national grid or a regional grid. So in fact, this pump turbine could be used as some sort of a shaving the peak or acting as a source of electricity during the no windy days when there is no wind farms. So this is an idea of coupling a hydropower plant to wind farms and making a network more stable, the electricity network more stable. There are many ongoing research and studies for these kind of schemes these days. Now we want to take a look to the turbine selection. You've seen this before through the Dr. Bridges lecture series. What I would like to highlight here is the dependence of the turbine type to the head range. We mentioned that the head is the most important factor in selecting a turbine and a power plant scheme. So you could see that for the very high range, high head, then it's Pelton, and then the Francis turbine, which covers more or less the very wide range of heads. This is the one that is used in larger scale hydropower plants. This chart here, if we take a look to this one, is the flow that available flow in cubic meter per second, and then the y-axis we have a head, different heads. So this region shows the applicability of different turbine types. If we take a look to this line on the right, which represents more than 100 megawatt, then we could see that it is dominated by Francis turbine. And then on the top of this chart, maybe on this area, is also some Pelton turbines that are used in larger scale hydropowers. But these projects are not that common. So mainly we will end to Francis turbine. As a designer, we have to pick and choose a Francis turbine. It's also very important to talk about the specific speed in the turbine, and this is a comparison of the different turbines without looking to their size, but rather looking to their geometry. So in order to define a specific speed, we should define a dimensionless group of variables, and this dimensionless analysis enables us to compare different turbines without taking a look to their real sizes. So here you could see 4 different dimensionless group of variables are defined here. It's psi, P, phi, and Reynolds, and they are each corresponding to one parameter of a turbine. So psi is the head coefficient, P is power coefficient, psi is flow, phi is flow coefficient, and Reynolds is the Reynolds number as it is defined in fluid mechanics. So the head and power coefficients, they are function of the flow coefficients. If you put the units for each of these definition in a consistent unit system such as SI, then you end up with a dimensionless variable. And these two dimensionless variables are connected to phi. This connection traditionally was calculated and modeled by hydraulic labs, making a smaller model of a turbine and then making some tests and then relating the results of the test to the real turbine. But nowadays, CFD or computational fluid dynamics is dominant in order to calculate that dependency. We will take a look to the CFD in our next series of lecture. Getting back to a specific speed, then a specific speed for a turbine can be expressed by eliminating turbine size d. So this is the specific speed. And if we relate these two dimensionless factors on this way, then we will be able to eliminate the d, which is the size or the diameter of the turbine. So here you could see that we end up with a dimensionless parameter without having a d inside it. And then in practice, it is very common just in order to eliminate rho, which is the density, and g, which is the gravity constant, and then write the specific speed as this term. It's very important not to mix up these two different and s values, because the second one is in fact dimensional parameter. Now, with the aid of the specific speed and the definition that we have, we are able to classify different turbines and compare them together. So here you could see the comparison of the turbine shapes with the specific speed. So we start from lower specific speed and then increasing the specific speed here. So each specific speed is now related to a specific shape as the turbine, as you could see. Probably you could notice that we are changing from the shape of the runner blades toward toward the cup line. So it looks like more like a Francis turbine here, and then it goes to the cup line. And in fact, it's true, because the impulse turbines, they are located below this range. So they have a specific speed of less than 45 in the units that we mentioned before. The radial flow turbines, which are the Francis turbine, they have a specific speed in the range of 75 to 380, which corresponds to medium head and medium to high flow rate. And then the axial flow turbines, such as a coupling turbine, then they have a higher than 380 as a specific speed. And then all of this finally translates into the different turbine selection charts, as this one here. So you could see different specific speeds here. It's very important to always mention the units and the exact formula which is used in the specific speed, just to make sure that is this the dimensionless or is it the dimensional parameter that we are talking about. So here you could see the increase of the specific speed and also the changing of the turbine geometry. It's not related to size, it's related to geometry. So you could see that we are moving from turbine which is from the impulse turbine, which is suitable for high head, toward the lower heads, and then changing the geometry toward this bulb turbine. So we can see the Francis turbine, which is in the middle range of the specific speed, which dominates the larger part of this chart. Now we have looked to the different type of turbines, and we have looked to the turbine selection charts. Now it's time to move to the more broader aspect of hydropower and take a look to the system characteristic and system performance of the large-scale hydropower by itself. Thank you.